Hello, everyone. My name is Yuval, and today we're going to talk about streaming real-time data into Iceberg. Now, Iceberg, as you all know, is really taking off across all the industry, and it brings a lot of advantages, but also it brings some challenges, especially with streaming real-time data use cases. So we're going to talk about them today, the popular challenges and also how to solve them in your lakehouse already. So let's start. So first, a bit about myself. I'm Yuval, the CTO at Rift, where we basically build an Iceberg management platform. So we see a lot of real-time streaming use cases and see a lot of these challenges in real life. So I'm sure you all seen this picture 1,000 times, but just as a recap, Iceberg is an open table format that allows us to describe a table using a set of metadata files and data files, and gives us an abstraction that gives us stuff like asset transaction, time traveling, schema evolution, partition evolution, and etc. And this image is important because all of these metadata files and the connections between them are going to be really impactful when you talk about streaming use cases. Before we dive into that, let's talk for a second about how do we even stream data into Iceberg and what tools are available for us today. So really, if you look at the beginning where Iceberg kind of emerged, basically there was only one tool, Spark Streaming. It's still very popular today, and it was the original tool that allowed us to stream data in real time into Iceberg. As time went by, more and more engines started supporting it, notably Flink, Trino, even Kafka. And then later on, even closed source engines such as Kinesis and Fivetran and Rising Wave and Stream Native and so many other engines that allow us to stream right into Iceberg today. So the amount of tooling is really varied, and there's a lot of support currently today, and new tools are being added every day. Now let's talk about how does streaming look like behind the scenes. So really, when we talk about streamings, we have two modes of operation. The first is appends, which is the most popular streaming operation. Appends is basically only inserting values inside a table without deleting, without updating. And what that gives us is, as you see on the image on the right, basically each point in time here is a new insert that, for example, happens in a streaming micro batch. So imagine something happening every minute or every 5 minutes. Each one of those snapshots creates all of this list of metadata files that you see here. So a new metadata JSON file and a new manifest list file, new manifest entries, which point to the new data files that are being created. So each of those inserts actually create a whole set of those files here. The second mode is actually an upsert. So you can imagine something like a merge into, where you want to either insert or merge existing rows. This looks exactly the same, and even in merge, you're still creating new metadata files, new manifest files. The only difference is that in some cases, you're going to delete the original rows that already existed that you want to update. And that happens in a few ways, and we're going to talk about it later in this session, but basically imagine as you're deleting existing files and at the same time adding new files, all still while creating new metadata JSON, manifest lists, and etc. Now let's talk about really the main challenges that almost every organization that's streaming into Iceberg see. We're going to talk about small files, active storage, and merges. So let's start with small files. Small files is really the first problem that you're going to encounter. Basically, as you can see in this diagram, when you're starting to insert many times in each minute or each hour or each day, you end up with this very wide tree of manifests and data files. So you end up with a lot of manifests and a lot of data files, and they're all quite small. And this kind of have a trickling down effect, which really makes a bad impact on basically every query engine. So first, imagine that for each query, you need to make a lot of round trips to S3 or your cloud storage just to read some small amount of information. So both performance hit and both a high cloud storage API costs. The second thing is the high number of manifests specifically can result with suboptimal planning latency. And what that means is, imagine you're doing select star from a table, and just the planning phase, without even reading data, start taking time. So you're going to get this loading indicator without even the query starting, because it needs to read all those manifests to even understand which of those data files underneath do I even need to read to scan in order to find the queries that you're looking for. Other things are things like Parquet compression and Parquet metadata that are kind of suboptimal when these are divided into so many little files. And also task orchestration is actually a really big issue, where imagine that if you're reading something like Spark, you basically end up using a lot of Spark tasks and a lot of CPUs or threads in parallel to try to read all of those files in parallel, which results with a lot of overhead, a lot of memory overhead, and basically just a slower operation. This is one of the kind of biggest issues that you end up if you're not handling those files correctly. Now, to solve that, of course, what we have in Iceberg is data compaction, which is really important and crucial to run in order to have string operations run smoothly. So compaction is very simple, right? You take a bunch of files, small files, you merge them into a lower amount of files and bigger files. So you end up, for example, in this case, instead of 5 files, you end up with 2 files. And then the engine, where he needs to read those files, he only have to read 2 files, and they're large and have good compression and good metadata. So that's, of course, a really good solution. However, compaction in streaming is actually a bit challenging. We can take a look at a few examples here about how your compaction strategy can really impact your cost and your performance. So on the left here, you can see basically 10 data files. Each of them are 1 megabyte. Now, what we're going to do is we're going to wait for those 10 megabyte files to be on disk or on S3, and then compact them into one 10 megabyte file. So if we measure that in what we call bytes compacted, we can see that we took 10 megabytes and compacted them. So we have 10 megabytes of bytes compacted. On the right, however, we're going to run that after 2 files, we're going to run compaction. And then after 2 more files, we're going to run a compaction again, and et cetera, and et cetera. Now, so basically, we're not going to wait as long as the left side in order to compact. We're going to compact early. Why is that really good? Because if the data is being queried as it's being written, very high SLA, low latency data, then everything is getting compacted and the current queries can be faster. However, if you look at the math here, you can basically see that we're compacting so much more data, because we're compacting the same files over and over again, because we're very eager with compaction. We take 2 files, we compact them, and that result gets compacted again with the next file. So in this case, we're actually compacting 44 megabytes. Now, these numbers are pretty small, but imagine much higher numbers can result with very costly operation of compaction. So this is just a demonstration how 2 different strategies in compaction can really affect the amount of compute you actually need to allocate to actually do that. Now, when we're measuring compaction, we can actually try to measure it with those two axes. So the first one is compaction cost, as we just saw. And the second one is how many small files are actually being read. And you want to make sure that your compaction is as cheap as possible, but you also want to make sure that you don't read a lot of small files to avoid performance hit and query costs. So you can see how for different use cases, you can kind of move along these axes and understand where do you want to spend more compute on compaction, where do you not, especially with regards to how is the data actually being read, right? You want to maybe compact tables differently according to, are they actually used? Are people querying only recent data, older data, and etc. So this is kind of a good mental model to have when trying to understand compaction, especially in streaming use cases. Now, a few important considerations are actually, we can divide them into when do we want to compact and what do we want to compact. think this really helps kind of understanding the algorithm that you want to choose eventually. So when talking about when to compact, a few important things here. And the first is actually counterintuitive. It's actually when not to run compaction, right? The easiest thing, the easiest optimization is just not to run compaction at all. And that may be in unused tables or really old data or things like that. In terms of strategy, you can think about strategies that are based on commits. So after a number of commits or snapshots, or maybe amount of files accumulated on disk, or something that is more time-based, so you can compact every a few minutes or hours, depending on your use case. And of course, a combination of those will probably give the better result. In terms of what to compact, this is also really important. So if you think about you have a limited number of compute, you probably want to prioritize what you're compacting first. Now, you can prioritize both entire tables and parts of tables. So in terms of tables, of course, you want to compact the most used tables that your users will feel the impact the most. You don't want to spend a lot of time compacting unused tables, and then in the meantime, users are querying kind of the popular tables and not enjoying the benefits. And the same thing is true for partition priority. So a table, for example, a time-based table that maybe also have late arriving data. So you need to kind of choose, am I compacting the data from a few days ago, or am I compacting the data that arrived a few minutes ago? And you can, depending on the use case, you can even prioritize the partition to say, for example, let's first focus only on the most recent partition. So we really want to make sure the last day is compacted. And if we have time, we move over and start compacting older data again, just to make sure the table is healthy. So you can see, compaction seems pretty simple on the surface, but actually all of these considerations, especially in streaming, because the data is updating so much, becomes a bit tricky. And I think this is a good mental model to have when thinking about the algorithm to compact. Let's move on to the next issue, which is what we call an active storage. Now we can define the active storage as the size of the current snapshot of your table, divided by the size of all the tracked snapshots in the current Iceberg tree. So basically, if you say, for example, 100 snapshots, and some of the snapshots reference files that do not exist anymore, these still take up storage on disk. We can even enlarge this definition with not only everything in the track snapshots, but basically everything in the bucket at all. And what you want to make sure is that the size of the current snapshot, which is actually the data that your users are using and exposed to, is not too far from the amount of data on the bucket itself. And that's what we call the active storage. And we usually recommend aiming to have an active storage of, for example, 70, 80, 90% in healthy situations. Now, let's see an example. So imagine we have the same example of 1 megabyte files in streaming use cases. So we have 1 megabyte file and then another one, and then we perform compaction. So now we have this green 2 megabyte file, which is the compaction result. And then we have another file coming in the next micro batch. The same thing happened again, and we have now a 3 megabyte file and another file coming in again. So what you can see now is that the tracked snapshots actually contain 9 megabytes. But if you look at the latest snapshot, which is what the users can actually query, they only have 4 megabytes. So basically, the active storage in this case is actually just 44%. That means that 66% is storage that is on S3 right now, or your cloud storage, and you're paying for it, right? So the active storage is usually most painful kind of in your wallet. But again, in these numbers, it's pretty small. Imagine instead of 1 megabyte, this is 1 terabyte. Now the numbers become bigger and bigger, and we actually see lakehouses where people end up paying tens of thousands of dollars just for data that resides on disk and they're not actually using. So in streaming use cases, you really want to fine-tune snapshot expiration to make because streaming creates such an aggressive and high number of snapshots as streaming comes into a table, that snapshot expiration can be even highly tuned and more aggressive way. Now let's move on to the last challenge. which is merges. Almost everyone that is streaming into Iceberg gets to a situation where he wants to merge and kind of encounter a very slow operation or trying to optimize it, and it's a really, really popular problem. The problem with merge is actually it contains a read query and a write query, because you want to understand what data exists today, and from that decide if you want to update or insert. And you can see kind of a diagram on the right on how that looks like. So you start by scanning, partitioning, applying all of your filters, and then joining this data together just to perform the final overwrite operation. A very interesting optimization that was added to Spark lately is something that I want to talk about right now. Is called storage partition join, or in short, SPJ. Now, this is a really handy trick to see if you can have in your active in your lakehouse today. SPJ is a specific optimization that works well with Spark and Iceberg in partition tables. So on the left, you can see how it looks like without SPJ. Basically, two Spark executors try to perform this join operation, which starts by shuffling data between those two executors. Why do they do that? Because they need to make sure each executor only holds specific set of partitions so they can scan them and then join them. And as you all know, shuffling is one of the most costly operations in Spark, both in memory and in runtime and etc. What we can do is, if we're merging two tables that have a similar partition spec, what we can do is actually let Spark optimize that and avoid the shuffle stage completely. So basically, you can see on the right how it looks like, where every executor know exactly what partitions it already have, and those partitions actually match. So now he can avoid that costly stage, perform the filtering as usual, and then join much, much faster. And you can see that if you look at the Spark plan of your queries to make sure that SPJ is actually taking place, because the results can be really, really impactful. Lastly, and this is super important, is the write operation that you define for Spark, and this is especially important for merges. So in Iceberg, you have two write operations. One is copy and write. The second is merge and read. Both are pretty straightforward, but it's important to understand what are the trade-offs here. Copy and write means that if you have a query, like you see here, that is merging into a specific table, and for example, you want to update the timestamp because a user has done an operation and you want to maybe keep the last updated time for each user. What you can do here is actually just replace the entire data file that is relevant for that user. So you have one row to update. You look for the specific data file that needs to be updated. You create a new data file that is exactly the same with this row updated, and you write it again. On the right side, you can see how merge and read looks like. Instead of replacing the file, you're actually creating another file, which is just a delete file. And the delete file is a small file that just points to the data file, in this case, data file 2, and tells the engines, hey, this row needs to be updated as follows. Now, what are the trade-offs here? So in merge and read, you can imagine that now if an engine comes to read that data file, he needs to do some extra work, because he needs to see that there is a delete file. We need to merge those two and return the updated results to the user. So there is much more latency and runtime needed on the query side. On the left, this runtime still needs to happen, but this happens on the right stage. So there is more latency on writing, but for the query engine, there is very little work to do, because it just needs to read the data file without extra processing. In streaming situations, sometimes copy and write can be very costly, right? If you're streaming tons of data and you're trying to get the latency very, very low, replacing all of those files, if you have a lot of updates, can be very, very costly. And sometimes using merge and read can actually be beneficial, because you can write it really, really fast, not replacing huge amounts of data, and keep a low latency. Of course, if you're choosing merge and read, you have to accept one of two situations. Either you're okay with having the query engine do the extra work while querying, or you're orchestrating an asynchronous operation of something like compaction that we talked about before to make this to merge this data file and delete file afterwards to make sure that the data file is actually ready for really optimal reading. So this is kind of a way to balance the two, right? Have a very low latency in writing, but also making the life easier for the query engine. So there's no right or wrong answer here. It really depends on the use case, but it's this setting can really affect your streaming latency performance. Also in merges, something interesting to talk about is commit conflicts. When not doing merges and just doing inserts, there's not really a lot to conflict about because you can just add more data files, and even if you have a conflict, you can resolve it very easily just with metadata operations. But with merges, if you think about the diagram here, we have a merge operation happening that needs to replace some data file, but we also have the rewrite data file, which is basically a compaction job writing on the same time. So they both kind of compete on replacing the data, and one of them has to wait for the other for the data integrity to actually work. And then what you end up having is write failures, either on the compaction part or in the streaming part. If you have a batch job happening once a day, this is not really a problem. But once you stream every minute or every 5 minutes, this is a very popular situation to have. So basically, there is no magic answer on how to avoid that, but you really need to make sure you schedule your maintenance job accordingly, and not having something too basic as run every minute, because the chances that you're going to have these commit conflicts and failures is very, very high. So you need to orchestrate your streaming jobs and your compaction jobs together. Also, this is something you can track with metrics and kind of have alerts on, and etc. And this is really recommended. So just to end up here, a few really important takeaways. First of all, streaming with Iceberg can be somewhat intimidating, but actually it's really well known. It works really well. It gives a lot of benefits, and tons of companies around the world are doing it. So don't be afraid and kind of keep streaming. A few things to note is first, measure your compaction, because compaction in streaming use cases can be really, really costly and kind of explode really fast. So be smart about when do you compact and what do you compact. Monitor your active storage and perform a smarter or more aggressive snapshot expiration strategy to avoid paying a lot of storage costs, and really aim for that 85% of active storage in healthy situations. And lastly, if you're doing merges and you don't have any way to avoid that and just do inserts, you just make sure you tune all of the right settings. Look at copy and write versus merge and read. Schedule your maintenance job appropriately, and look at the Spark plans to make sure that SPJ is working for your merges if possible. Thank you all very much. Appreciate you being here, and have a great rest of the summit. Thank you all.
Awesome. That was great content, Yoel. I really enjoyed the session, and I hope the attendees did too.
Thank you so much.
Let me check if there are any questions. So this will be a good time to post your questions in Q&A, and we can go through that one by one. Yeah, and as I shared before, this recording will be shared with you, post the event. So you can go through that slowly. I personally feel that in a lot of content, what you shared is kind of, it's worth revisiting and listening to it again, and, digesting that slowly in terms of, and reflecting on what are the areas which make sense for you, particularly the compaction piece, right?
Yeah.
So, for sure. Okay, let me see. I don't see any other questions, any questions so far, but any comments you want to add additional to what you covered, for our audience today? There's a lot of exciting
Um,
things going on in the world of Iceberg, so and that's why I see a lot of attendees have joined your session actually today. But
Yeah. Yeah, I just think, Iceberg is becoming super, super popular. And I think that companies with like with real-time streaming use cases are kind of thinking, is this right for me? Or do I really need to use, something else, a time-based database or something like much more complicated? And in reality, we actually see real-time use cases being adopted a lot by company with Iceberg. It's just that it requires a bit more tuning, a bit more thinking, and that's what I kind of try to lay it out in the session, especially around compaction, which is the most important part with streaming. But other than that, Iceberg shows tremendous results with real-time streaming, so that works well.
perfect, awesome. I see there's one question here. It's possible. Is it possible to clean snapshot history to reduce size or cost in storage?
Yeah, it is definitely, it's not only possible, it's actually highly, highly recommended. And as I mentioned in the session, what happens sometimes in streaming, you may tweak your table so maybe you expire snapshots after, for example, 5 days or something like that. The problem is that if you're streaming, then imagine how many minutes, if you're streaming, for example, with 1 minute micro batches. Imagine how many minutes are in 5 days. That's kind of like almost 10,000 minutes or something like that. So that's 10,000 snapshots that you're saving. So I would actually recommend not using a much more aggressive strategy. So either reducing the number of days or actually using an absolute number instead of a number of days, use an absolute number of snapshots. So for example, say I just want to save 100 snapshots all the time and that's it pretty much, because otherwise the storage and metadata are going to explode. So yeah, definitely recommended.
Well, that was a great question, actually. Yeah, lovely. Um, cool. Let's see if there's any other questions. I don't see any. Um, I know there is, particularly what is really helping. What I notice about the iceberg community is like, everyone's kind of very much excited to be a part of this journey of even if like any part of that touches and makes sense to really have a support for iceberg. Everybody's really excited to have that support, and all these sessions are so helpful because I think this is one way to share best practices around how others are doing, and then we learn from each other. So I think definitely um, exciting times we are in right now when it comes to these open data table formats, right?
Yeah, for sure.
Okay. I know I don't see any other questions. I'll give another 10 seconds to see if they want to post any new. But if not, I think you'll all be getting a recording of the session. And yeah, I think the next session, perhaps I think at least for the deep dive, is the last one, which starts in a few minutes. So you'll get 5 minutes of break before that. So I don't see any other new questions here. Great. So, anyways, thanks so much again, Yuval, for your time, and it was great content. I know I will go back and listen to that session one more time in the recording, and I'll basically request the rest of the attendees to stay tuned. We have more sessions going on, so feel free to join them. But have good rest of your day, and we'll stay
Thank you so
connected.
much for having me.
Thank you so much, Yuval. Thanks.
Bye bye.